Hey, everybody. Um, so quantum computing is not merely a new form of supercomputing. It's about technologically accessing a vast and normally hidden reality. And if successful, could produce unimaginable computing power. But why would you want to do that? Don't we have enough already? I think it's really important for people to ask all of the technologists and scientific community. Oftentimes people will work on things because they're cool, because they can profit from it, create new markets. But a really important question to ask yourself when you embark on any enterprise is, what kind of world do you want to live in? When I was growing up, that's the world that I wanted to live in. And in watching Star Trek, they used to refer to this time in human history where our cleverness was outstripping our wisdom. And they talked about a time of our technological adolescence. We have the emotions of Neolithic beings, some medieval belief systems, and godlike technologies. And this is a really potent recipe for disaster. And so, one, you have to have very deep understandings of the world you live in and the systems that you're building. And two, you have to have a profound ethics. And in this world, they had just barely gotten through that technological adolescence. And I realized as I grew older that that technological adolescence was my time. We've built a civilization of staggering complexity. And what is often misunderstood or certainly underappreciated is that this gives rise to problems that transcend all human understanding. So in every area of human endeavor, whether it's energy distribution networks, defense networks. This is interactions between drugs and human biology. You can model a lot of these systems. You have very many elements that interact in incredibly complex ways. And what this allows for, you have these staggering complex systems, and it allows for vast inefficiencies because we don't know how to model them accurately, and the best way to arrange all those parts and interactions to get a desired outcome, and the potential for incredible system crashes. So if you look at financial systems now, lots of computing going on, lots of fast trading. It's possible that with a certain set of inputs, you could crash entire systems and no one would know why. And this happens all the time. So what do? Don't we have computing resources at our disposal to handle all of this? We have what I call network brains. Everybody's networked. All the scientists are talking. You've got there's a Google data center. We're generating data at unprecedented rates all around the world. We have machines that can learn from experience. Isn't that enough? And the answer is no, provably no. And why is that? So there's classes of problems. There's a field called complexity theory wherein you want to characterize how hard a problem is to solve. And problems that we typically call tractable scale a certain way. So the best way to define the complexity of a problem is how much harder does the problem get as you grow the problem. So let's say you double a problem, it takes 4 times as long. That kind of goes up like the square. Problems like that are called tractable. But most of the problems associated with these very complex systems, for small changes in the problem size, you get an exponential explosion of the resources required to understand and solve those problems. A mundane example would be something like FedEx. I want to route all these packages. The number of routing strategies explodes exponentially with the number of nodes and cities. And all of a sudden, and you'd like to say minimize fuel consumption. No one can solve that problem with all the supercomputers on Earth. For simple molecules, I was talking about modeling matter earlier. You can take relatively simple molecules, and the largest supercomputers on Earth can't calculate their dynamical behavior in time. Building accurate models of the world, machine learning. You hear about this. Right now, most machine learning is classifying and doing what's called regression. What it's not doing is generating models of the world. What would be really nice is you have lots of data, whether it's a healthcare system, or about making better materials, much more efficient solar cells. And if I could take a lot of data, and that system, like a human, could see patterns and build a predictive model so that we could make better decisions, this would be an amazing thing. But even this is an intractable mathematical problem right now. So historically, when we've had big problems, humans have found ways of harnessing new resources in nature. Here's some big ones: fire, agriculture, industrial revolution, electronics, nuclear physics. We didn't make very good decisions about what to do with that. Rather than using it to make sustainable energy sources, we figured out how to vaporize other people's cities. But interestingly, in all these revolutions, there's two phases of these revolutions. First, we find a resource and we use it, but we don't understand it. We don't know how to create it, control it. And then there's a second revolution, say, with fire, where we learned how to make it. Maybe I put a bellows and I could make it hotter and smelt metal. Or in agriculture, to cross-pollinate plants to make more robust species. So there was a revolution in the early 1900s. It's called quantum theory. When people first started looking at the behavior of atoms, electrons, they found that they weren't just miniaturized versions of what we experience in our own lives. They found very bizarre behavior. They found electrons behave as if they're sometimes everywhere at once, living out multiple possibilities. And they didn't, a mathematical theory was put together that characterized these behaviors, but a true understanding of what this said about the world was kind of lacking. Nevertheless, it was like the early days of fire. People said, well, the equations work, I can predict atomic behavior. With it, we were able to explain why the sunshine, the fusion reactions, gave rise to the silicon revolution, band gaps and transistors, laser technology, nanotech, an understanding of nuclear reactions. And so you said we have this, the deepest understanding of nature we have right now is quantum theory. But I call it the shut up and calculate decades. Nobody understood what does it actually say about the world, and like with fire, if we really understood what quantum mechanics said about the world, what would it allow? What new possibilities? Well, I'll tell you, over the last few decades, a much more profound understanding of quantum mechanics has come to the fore, and it's allowed for some tremendous possibilities. So one is this idea that an electron, say going from point A to point B, unlike you walking from one place to another and taking a specific trajectory, could instead take multiple paths. Every possible path available to it, it actually realizes. And if you think about that, let's say you want to get through a maze. Well, you try one path sequentially. What if you could try all the paths simultaneously and those paths could communicate with each other? So I'm going to give you an example. If you remember nothing else from this lecture, I'll tell you quantum computing in a nutshell with a prosaic example. Imagine I go to the Library of Congress, and there's 50 million books or so. And I put one book off a shelf, put an X in one of the pages, and put it back. And I asked you, go to the library, find the X, you got 5 minutes. Of course, you're going to say, well, this is a ridiculous enterprise. Unless I get incredibly lucky, I'm going to take one book, look through it, the next one sequentially. But if I said, but what if the world was like quantum mechanics suggest, really? And I could put you in a parallel set of parallel universes, 50 million of them, and in each one you choose a different book. You take a different alternative. Great. There's another strange aspect of quantum mechanics that when these systems are doing all that, if I open the door to ask, I'll encounter one of you with some probability, likely someone who didn't find the book. But this problem has been solved, David Deutsch at Oxford in the 80s, by something called quantum interference. Imagine you could talk to all your other selves in all the other libraries. So the version of you that found the book lifts it, says it's page 365 of this volume of Shakespeare. That information is shared across all those parallel branches of reality. And now when I open the door to the library, it doesn't matter who I encounter. They have the answer. So you've done in seconds what would have taken lifetimes. That's quantum computing in a nutshell. But I just told you something strange about the world. If there's this multiplicity in nature, and you're built out of those fundamental elements, how come you don't experience the world that way? This wasn't well understood for a long time, until the 80s and 90s with a theory called decoherence, which is just quantum mechanics. So I'll try to give you another prosaic example. So if there's all these branches and they're collaborating on a task and you get this amazing computational advantage, what disrupts that computation? So imagine the windows to the library are open, and one of the versions of yourself is kind of hungry and sees a restaurant across the street. You know, screw this, I want to get a bite. Another sees a theater with a movie they really wanted to see. They go to that theater. Another one sees a pretty girl. And so what'll happen is these interactions with the external environment will pull those streams apart in such a way that they can no longer collaborate and solve that problem. So it's when people took interactions with the environment, in the case, say, of this clicker, unlike an electron, has lots of air molecules bounding into its surface, lots of photons of light. It's in my hand whose atoms are wiggling. And when you put all of those things into the Schrodinger equation, you'll see how those different branches diverge or decohere. So how do you keep coherent evolution where those different branches of reality can communicate to solve big problems? So what do? In my prosaic example, how about you close the windows to the library? And now there's no external interaction. So in the case of this, what if I got rid of the air in the room? Ultra-high vacuum. What if I shielded it from all the radiation? What if I somehow froze myself and went to very low temperatures so there's no fluctuating atoms? Well, people have done this. And in 2000, let me go here, a ring of superconducting material was taken to ultra low temperature, shielded from radiation, all the air pumped out, and under the right conditions, they saw a macroscopic object live out two branches of reality that communicated with each other. In this case, I have a superconducting ring, all of an electrical current going clockwise in one branch of reality, and all the current in another branch of reality, but with the same physical object, living out these two alternatives. And there's a very unique signature of them speaking to each other, something called an energy gap. Now we see quantum mechanics at macroscopic scales with objects you can see with your naked eye when you create the conditions to keep coherent evolution. So all over the world, after people saw these effects in a multitude of systems all over the world, the race was on to build quantum computers. Actually, one of the things that drove this evolution, again, speaking about ethics and being careful, so this is the description by one of the fathers of quantum computing, that it's a way of using parallel universes to do computation. What scared the world into starting to fund this field was this gentleman's algorithm, a guy at Bell Laboratories, computer scientist, mathematician, Peter Shor, and he showed that some of our most powerful encryption methods, like RSA, that would take billions of years to break on a supercomputer, you could do in seconds or minutes on a quantum computer by using this parallelism. That paper got published in 1994. NSA, DARPA, all these agencies went crazy, said this could undermine our civilization. But what else could these things do? Let's start funding the field. All of the requisite basic phenomena have been shown in a number of different physical platforms. So for instance, ion traps. You float some ions in electromagnetic fields under ultra-high vacuum. You can put them in these states of being, say, a 1 and a 0 simultaneously. You can catenate them. So see, each one of these objects can be in two states at once. You want to build sort of robust technology. You put simple elements together, each of which can explore a couple. You can catenate them, and you can explore an exponentially growing number of possibilities, just like the exponential growing possibilities in the problems we want to solve. But those are tough to build because they're microscopic. So the company that I helped form, D-Wave, we took these rings that are macroscopic, superconducting materials. There was already an infrastructure for building non-dissipative circuits that keep the windows closed, to couple to those quantum objects and build things at scale, which we've done. Another just quick comment is that I used to run a big government program. I was also at an aerospace company that was doing this. And when I looked at what was going on in the world, most of these companies had very short-term visions, looking at quarterly profit returns. The government projects often were ill-funded. These kind of loose associations of a lot of different researchers. It wasn't efficient, so we decided to make something like a mini Manhattan project, a D-Wave. I've seen that, it used to be there were Bell Labs, of the world. They're not around so much anymore. Big companies are looking for short-term profits more often than not. It's small companies with entrepreneurs taking big risks in big areas to solve big problems. These are characteristics associated with successful companies, and there I've got places like Celera Genomics and SpaceX. So we built that kind of company. We built a processor at D-Wave. You can see here each one of those little dots represents one of those rings. When current goes one way, you get a magnetic field that's a 1. Current going the other way, it's a 0. We can put those in states where they're both simultaneously. We have them interact with a bunch of other objects. Those can represent correlations in real physical systems. So it could be you're trying to optimize a financial risk portfolio, and it could be, you know, some things go up together or they're anti-correlated. I can program in correlations. This matrix can take on an exponentially growing number of configurations. Those configurations could represent routing strategies, investment strategies, energy distribution strategies, or the connections between neurons in a machine learning neural net. And you could explore a vast number of configurations trying to find optimum configurations. So one way to think about a lot of these problems is oftentimes people will draw these, what they call these complex energy landscapes. Each point on a landscape represents a particular configuration of these interacting spins. And if I were to put you in a landscape of hills and valleys, and let's say I call the deepest valley the best solution, the configuration of variables that gives you the best solution to your problem, you'd start somewhere and you'd have to start exploring that landscape kind of one at a time, like in the library. With these quantum systems, I can have a quantum system that will span the landscape and see the deepest wells and end up in them in vastly less time. This is an example with a lot of stuff going on in neural nets. They're very difficult to train. How do I arrange the interactions between the neurons to get the functionality I want? Speech recognition, pattern recognition, or more generally, how do I get them to generate models automatically from data sets that are too big and too complex for humans to comprehend? This is an example of a chip, what we call the unit cell. You can see we took that fundamental object, stretched it out. There you can see 4 horizontal qubits, 4 vertical qubits. Where they cross, they interact. Most of what you see there is a bunch of complex superconducting circuitry to program the chip, to read out answers, to evolve it quantum dynamically. You can see it has rather the structure of a neural net, which makes it nice for the machine learning people. We've taken that, and now you can see a bunch of unit cells, those little squares. That's the most advanced quantum processor on the Earth right now. But like I said, we have to shut the doors of the window. Shut all the windows of the library. So we put this in a very complex infrastructure. You can see radiation shields, all kinds of complex filtering. There's something called a dilution refrigerator where we go down to 10/1000ths of a degree above absolute zero. Reduced magnetic fields and radiation. We have now built commercial systems. You can see here that Google bought one of our systems with NASA, created the Center for Quantum Artificial Intelligence at Google and NASA. This is at USC and Lockheed. Had a collaboration, has a center around our materials, looking at a whole range of things, everything from software validation of very complex systems, pattern recognition, neural nets, even search for exoplanets by looking for small fluctuations in complex, noisy data. And in terms of like a really significant result that was just confirming the physics, Google basically built something like a maze, a set of barriers you'd have to figure out how to get through. They ran a data center with millions of processors for, say, a few weeks until the people in charge said, shut that down. We got through the maze 100 million times faster. So this was a proof that that physics of multiplicity and also appearing on the other side of barriers you don't pass through, calling quantum tunneling, was present in our chip. And the largest supercomputers on Earth right now have about 3 million cores. That doesn't mean they're 3 million times faster than a single core, because it doesn't really scale that well. So this portends a future where you might be able to solve very large-scale problems. There's a nice quote by the head of AI at Google who said, you know, with the Wright flyer, the Wright brothers flyer, barely got off the ground, but it flew through the air, which is something humans had never done. The D-Wave processor flew through these parallel universes to get an answer. A historic event. That's the actual data. And I think we're at a tipping point. We now have shown that for synthetic benchmark problems, we're seeing our quantum processors exceed what you can do classically. They're not at the stage yet where we can put large-scale industrial scientific problems on there. We think in the next few years we'll get there. There's a global set of researchers, IBM, Intel, Microsoft, a bunch of startups I'd like to hope we inspired. Research going on all over the world to kind of harness this new resource of this hidden reality. And we've been on at D-Wave, we've been on something like a Moore's Law or even better trajectory in building larger and more powerful processors every generation. The first physics book I ever read was by this guy, Paul Davies, that got me into physics. This is his opinion that the 19th century was known as the machine age, the 20th century is the information age, and I believe the 21st century will be the quantum age. Again, I think it's important. This is an extremely powerful resource. I think as a civilization, we've built systems that transcend our understanding. We either downsize a civilization and get simple. You've seen nothing but more complexity being promised at conferences like this. To really understand those systems at scale, to be able to model them, to do the right things with them, we're going to need much better tools. And the only tool available that can capture this kind of exponential complexity is accessing the multiverse. Anyway, thanks. I think that's it.